up there at the top. And what I'd ask you to do first is just to read the 5 bullet points that are up there at the top, just some things to keep in mind. And while you're reading through these, I do want you to think back to that TED Talk that we watched in class, specifically about the difference between false positives and even having a good test. There's still things that can be skewed. Okay, so I guess we want to read these next 2 bullet points too. So Bayes' theorem is going to keep all of this information in mind. It's going to correct for some errors, and it's going to say, all right, you get a positive result. What's the probability that you actually have the disease, or something along those lines? So let's look at these examples, and that will kind of help us look at what we're using here. Here's the information that you know. 1% of women have breast cancer. 80% of a mammogram will detect breast cancer when it's there. That's a true positive. It's going to detect the breast cancer, and the breast cancer is truly there. However, we have 9.6% of the mammograms are going to detect breast cancer when it's not there. Those are our false positives. So what we're going to do is we are going to, let's put some things in the table here. And actually, I just don't love the table because the table doesn't really work the way we want it to. So let's skip the table for now. And let's look at, in part A, let's go ahead and just make a tree diagram down there in that space that we're given. And then we'll be able to answer the question. So the first thing that occurs, we have to decide if having cancer occurs first or if getting your test occurs first. And which, really, I guess the question is, which is dependent on the other? And in this case, your test is dependent on whether or not you have cancer. It's not that you would get cancer from taking the test or something along those lines. So the first thing that we want to put here on our tree is whether or not you have cancer or no cancer. So this will be actually does this person have cancer or not? And then we can have from there, you could get a positive test or a negative test. And then same thing here, a positive test or a negative test. And there's different percentages based on whether or not you have cancer. Now we know that 1% of women have cancer. So we'll put their 1% here. That means that 99% of women don't. If they have cancer, using a conditional probability here, 80% of the time the mammogram is going to detect breast cancer if they have it. So that's where my 80% would go. I assume that this person has cancer. 80% of the time, they're going to have a positive test. Now, a negative test is going to occur the other 20% of the time. 9.6% of the time, you'll get a positive test even when you don't have cancer. So this is going to be a positive test with no cancer. And then the other part, the 0.904, would be a negative test with no cancer. What I like to do at the end of my tree diagrams is I like to just go ahead and multiply through all of the branches. So like I would multiply the end result here, and that would be the chance that someone A has cancer and B gets a positive test. Since both of those two things have to be true, I'll use the multiplication rule and I'll multiply those two things together. So I'm going to go ahead and multiply down here to the end, and I'm just multiplying down my branch and putting in the 4 numbers here at the end. So these numbers that I have there, those are the numbers, for example, this first one right here, this would be the percent that someone has cancer and gets a positive test. This down here would be the percent that someone doesn't have cancer and gets a negative test. So it's when both of those two things are true. So what we want to do is we want to say, all right, this person gets a positive test result. What are the chances that they actually have cancer? Because we've seen those things that are false positives. So what I'm going to do is I'm going to decide which of these end results are considered a success. And in this case, a success is having a positive test result. So both of these two events here are where we get a positive test result. Now, before we get any further, let's go ahead and mark which of these results are where the test is doing its job versus where the test is not doing its job. So for example, if you have cancer and you get a positive test, that's good news. Well, it's not good news, but that means the test is doing its job. You have cancer, you got a positive test, the test has done what it's asked to do. If you don't have cancer and you get a negative test, there's the good news. No cancer, you get a negative test, the test is doing what it's supposed to do. All right, and then these other two options, if you have cancer but you get a negative test, that would not be good. We would want to detect the cancer. And if you don't have cancer but you get a positive test, again, that would not be good. We want to detect that you don't have cancer so we don't falsely send treatments. All right, we put stars next to the things that are considered successes. So let's go ahead and think about what the question is asking. So I'm going to go ahead and turn this into math. I am assuming in this case that I have a positive test result, and I want to know the chances that this person has cancer. The extra information that I'm privy to is that the person got a positive test. That's what I know. What I don't know is whether or not they actually have cancer. So what we'll do is we'll say, all right, so we want the probability of cancer and a positive test over the probability of a positive test. The probability of a positive test, I need to add together those two that I've starred. And we've said before that whenever you have a conditional probability and you find the number in the bottom, you're going to find the number in the numerator just by, that's the way it's calculated. So the number in the numerator should be one of those two values that we starred. That's when you have cancer and you get a positive test. That's the very first one up there. And if you can go ahead and plug that into your calculator, that's the value that you get. This is the chance that someone who has a positive test result actually has the disease. That's less than 10%. Now that doesn't mean, you get a positive test result. You could say, oh my gosh, guess what? I don't have the disease. There's only a 7% chance, 8% chance that I have the disease. That's just because that the cancer itself is actually pretty rare. Only 1% of women have it. So if everyone's getting tested for it, well, of course, we're going to have a lot of people who do not have this disease, who potentially could have a false positive. And again, think back to that TED Talk that we watched. This is the majority of what you will see sort of in this class. Now, we're going to take it just a step further. The stuff that we're going to talk about kind of from here for the rest of the video is not super important, but it is really useful in the real world. There is a formula for Bayes' theorem. The formula for Bayes' theorem is this. The probability of A given B equals the probability of B given A times the probability of A over the probability of B. It's just a formula, and we'll just kind of plug in some information that we're given. Do you ever get spam emails? I get them kind of a lot, or spam phone calls maybe. So what your email does is it has some filter, and it tries to filter out a lot of emails into your spam folder. So if you go on your email in your spam folder, you're like, oh my gosh, look at all these emails that are here. I didn't even know they existed because your email has already filtered them out. Your email uses this thing called Bayes' theorem in order to kind of filter out the filter out the emails. Now, sometimes you go to your spam folder and you're like, hold up, this is an email that I really needed. And your email has filtered it out, even though it was not technically spam. So it uses the Bayes' theorem, which I think is kind of cool. Let's move on to example 17, and let's talk about this last example here for Bayes' theorem. All right, so we're just going to take this nice and simple here. I want you to go ahead and read the question, and I'm going to put the formula for Bayes' theorem over to the side while you read the question. All right, so I have the formula, it's just the same one that we wrote over there. So I'm not going to even make a tree for this one because it kind of gives us all the information that we're looking for. So A is that the patient has liver disease. So 10% of patients who enter your clinic have liver disease. Actually, I lied. Let's go ahead and just sort of put the tree on here. So this 0.1 would go here, and the 0.9 would go down here. So it says, all right, 10% of the people who walk into the clinic have liver disease. And we want to know the probability that they have liver disease given the fact that they are an alcoholic. Okay. So this is the clinic, right, for alcoholism. And so the people who walk in, we know that 0.1 of them have liver disease. So this is going to be the probability of A given B. So there's my A and my B. So when I'm filling this into my formula, I'm told the probability of liver disease, the probability of A is 0.1. We know that the test for being an alcoholic, we have patient is an alcoholic, that's B. And we know that 5% of the clinic's patients are alcoholics. So the probability of B that goes in the denominator, that's 0.05. All right, and so we know that among people who have liver disease, 7% are alcoholics. So if I know that they have liver disease, I know that 7% of them are alcoholics. This is kind of taking my conditional probability and flipping it around. So this is where my 7% goes, the probability of B given A. If you type this in your calculator, you'd get 0.14. So this is, let's say I know that a person is an alcoholic. The chance that they also have liver disease is 0.14. Kind of a useful thing that we can do there with Bayes' theorem.